Sir is going to discuss the derivation of Black-Scholes formula.
Yeah.
So I request all the participants to attend the lecture and to get benefited from it. Sir, I thank you once again, and you please start the session now.
Yeah. Good morning, everybody, or good day, everybody. I hope you had a good first session today. So now we are going forward with the going forward with the derivation of the Black-Scholes formula. Yeah, that's more or less the introduction to finance, to the Black-Scholes formula. So we had introduced the Black-Scholes model, more or less assuming that the asset price is the geometric Brownian motion. No? So this means our model currently, so we have similar definitions like strategies, portfolios, martingale measures. Yeah? And we have also seen that there is a unique martingale measure by Girsanov transformation. We have to remove the drift mu such that also the risky asset has the same return as the riskless rate, namely R. Yeah? So when the martingale measure P star, the discounted process itself, yeah, is just, yeah, so this one, yeah, this is the simple as an exponential martingale, WT Brownian motion under P star. Yeah? This means, according to the general theory, we now do all pricing under P star. Okay, so this means we have shown that the Black-Scholes model, meaning asset price geometric Brownian motion with some drift mu, and you can see it can also be a time-dependent drift, so as long as the Girsanov transformation gives you a martingale, so fulfills what's called the Novikov condition, so that's the exponential martingale with this drift alpha, mu of t, let's say, minus r divided by sigma might also depend on t. Yeah, the same procedure can also be done for let's say, generalized Black-Scholes models. Yeah, so generalized Black-Scholes model, you start with asset price. Let's say your favorite statistician had said, okay, this one sigma t st dbt under P, then always with a good under reasonable condition on mu t and sigma t, we get always plus sigma t st dwt wt Brownian motion under P star. This means our pricing measure will always change the drift to the riskless one. But of course, the volatility is not changed. You see the volatility function is the same under pricing measure and under historical measure. As long as this transformation, this MT, is a martingale. This one, so the transformation is a martingale. When we now say true martingale, this means can be used as a density. Yeah? Then we do this transformation with MT, where we now replace mu t divided by ST, sigma t, and so on. Yeah? So we can have also what's called the generalized Black-Scholes model, falls also easily into this type of Gesanow transformation. Yeah, Gesanow transformation also exists for Levy processes with jumps, also exists for jump diffusions, and so on. So it looks a little bit more complex, but basically the basic idea, drift always becomes a riskless drift, and only the volatility or the diffusion term remains the same under the pricing measure. This later becomes important if we talk about implied volatility. Okay, for this, for the current tutorial, we keep sigma fixed. Okay, so we had these strategies, H star, and now we look at the completeness. Huh? So as I mentioned before, yeah, in this context of geometric Brownian motion as asset price, yeah, we have our Brownian motion, yeah, and we have this martingale representation theorem. Yeah, so this means every random variable, if you have a random variable in terms of mathematical finance, an option, yeah, and we assume that under the pricing measure P star, under the pricing measure, this is a Brownian motion, yeah, W Brownian motion. Here we more or less now consider everything under the pricing measure P star. Yeah, so if Z is quadratic is in L square, yeah, this means the second moment exists. E star Z square smaller infinity. Yeah. Then we have a progressive measurable process. It's almost like adapted. Such, we can write set, as a constant, so the expectation, plus a stochastic integral with respect to Brownian motion. And remember our claims, at least discounted. Our price is always the discounted. It's a martingale under P star, the price. If we take now conditional expectation, okay, from this we can read off actually the hedging strategy for each contingent claim. So we denote the set of square integrable random variables, ft measurable. This means measurable because ft is our basic filtration, and not the filtration, the sigma algebra, so the final point in time when we have a sink. And then we can construct from this representation theorem, we can construct a self-financing strategy. Then we have a self-financing strategy. Again, we just have to define H, construct H, such that the associative value process satisfies for all P star. Sure, that's a VT, that's a value. VT equals VT depending on age. That's a portfolio which we get if we follow the self-financing strategy each H bar. Then our VT looks exactly like this. And then we know that this VT, if we put here F capital T, so VT, we take small t equals capital T, so that's 0, that's 1, E psi F capital T. And since Ft is measurable, psi is measurable with respect to Ft. Ft measurable, psi Ft measurable, this means a condition means it's equals psi. So in this sense, we get our hedging, the portfolio of a replicating, this VT is then a replicating portfolio, and actually the price, the value of this portfolio is always this expected value. This we could have also known if we have proven the fundamental theorem of asset pricing for a Brownian motion in continuous time. We have just, in the last lecture, we have seen that the discounted process is actually a martingale. The discounted value process is a martingale with respect to the discounted asset value. And as we have seen, I showed this. So we have that we dxu equals sigma xu dw. That's all under P. So we replace dxu by sigma times xu dw2. So in order to prove this proposition, we need to find h and v 0 such that for d given by 6.2, it holds that this one equals the discounted claim. And this we get because we know that for set, this is then also in L2, it's also in C. We just need to know that's in L2, that's also a reachable claim. That's a reachable in the sense of it's a random variable where we can apply the martingale representation theorem to. This means we find a phi u. This we find because of the martingale representation. Every martingale, every random variable set can be. Okay, then we have to rewrite this. We have du here, also phi u. We want to have the sigma hu xu equals phi u. So here we solve for h. Phi divided by sigma xt. That's our hedging strategy. We have the general theorem, and here we want to write set, the discounted at final time. This one, you plug in this equation, that's what we look for. H, we want to look for H. We have just a phi u, so we have to solve here for HU. Okay, this means we have constructed our H, the investment in the risky asset, and we know that we find a financing strategy, put it like this, H0 financing, lending, borrowing, the money market account. So we find the H0 such that we can construct a self-financing strategy. And so we are done. Okay, then we have the technicality that we need martingale property and so on. That is actually a martingale. First, it's a local martingale because the quadratic variation is finite. Here, from this follows martingale property of T. Follows from it's a bounded quadratic variation. Okay, there are these particular details that hedging strategies must also be admissible, that they should be larger than a fixed constant. This means they must be bounded from below. That somehow to restrict arbitrage property. So if the option itself is bounded from below, then we have what's called an admissible strategy. I didn't go into this detail, but that's kind of the question like of in real application, like doubling strategy will give you an arbitrage, but you need, as I said, potentially infinitely resources on cash. This means if we have derivatives in the language of mathematical finance, which are bounded from below, then we define the Black-Scholes price as a minimal initial value required for its replication. And so this is a Black-Scholes price. That's the discounted at time t. At time t equals 0. That's our price we would charge if we write the, but of course the price process is the price of the replicating portfolio. Price of option, put it like this, equals value, but value and price is more or less the same of replicating portfolio. And since in the Black-Scholes word our P star is unique, the phi is unique, though also the hedge strategies are unique. Okay. That's so far the general theory. So, and so if we take now the simple situation where our option is what's called the European option, the payout depends on execution time, capital T. The first, I showed it already yesterday, ST is this exponential martingale. So this means W capital T is a Brownian motion. So here there's a price, again, discounted expectation under the risk neutral measure. So in this specific case, we have the Black-Scholes word. Here, we just need to know WT as a normal distribution. This parameter is these parameters. Okay, that's the same formula, yeah, we got in the limit, yeah, when we did the binomial tree and did the rescaling, like in the random walk, we also got the same formula in the CRR model. Yeah? It's the limit in this here of the CRR model. As I said, that's not by incident, that's because the entire model converges as stochastic processes, or its distributions on the measurable space, and the measure space. We look at these distributions is a space of continuous functions. That's what I mentioned. That's the Donska's invariance principle. Here we just say, okay, the limit of the price is the price in the Black-Scholes model. So if we have a path-dependent option, which depends on the entire path, like we look back options, max ST, something like this, the maximum value, which depends on the maximum value, which are also written, which can also be, they are also traded in the market, or average options, which are called Asian options, which depends on the average one. Do you know of every other options which have a kind of a geographic name? We have European, we have American, we have Asian. Have you heard of any other? One I didn't mention, and this is quite a lot traded. Anybody have heard about another option? I mean, this is a tutorial, so please be active. Yeah, there's
Yes,
somebody.
Passport option, look back option.
Yes, passport look back. This is also look.
Yes, but nothing
This
option.
look back is like this. Yeah, can you know can you describe a passport option?
Sir,
Yeah.
I heard only. I don't know about much
Yeah.
more about.
Yes, but my questions was the passport option. I even couldn't do it out of my head how a passport option is defined. But basically, it's a kind of an exchange option. You can exchange, you can select stocks and so on. It's like a broad portfolio management options, I would say. It's entire let's say set of options which are very flexible. But another one, it's not American, it's not European, but it's concerned with an island between Europe and US. Do you have you heard about this? Bermudian options.
Yes.
Do you know what a Bermudian option is?
No, sir.
So it's somewhere between, here you have US or America, however you want to call it. Here you have Europe. It's not, I haven't heard about a British option, but Bermudian island is somewhere in between Europe and so what is somehow in between a European feature and the American feature? So you have any idea? Here you can only execute one. Execution time. capital T. Execution time, any T in 0T. Huh? So any idea what does it mean to have a Bermudian option?
It may possible after some time we have like American option.
Yes, so it's in between. So you have a sequence of agreed times where you can execute. So you fix, let's say, k times where you can execute. And it's very realistic. You say, okay, every first day of a month. You can execute every time. You just have 1st of January, 1st of February, and so on. That's much more feasible than at any time. So it's somewhere in between. That's option which depends on F ST1 to ST. Also from a computational point of view, that's like a collection of European options. But nevertheless, in this sense, it's path dependent. And you can only execute once. That's if you have executed T1, you can't execute later again. So it's a Bermudian option, and so that's also common. Okay, but anyway, what you have to do then is to calculate this expectation. So this now you have to simulate, or you have to get the distribution of the entire path. So, but just one important remark as well here. In this simple Scholes model, the only parameter which is somehow free, like interest rate, you agree that's like the overnight rate or whatever. You, in order to get the price, there's the current price we know. It's a quoted price. The maturity, capital T, we know. The only free parameter is sigma. Okay, and we come later back to this, how this is transferred to the quoting of options in implied volatilities. I don't know whether in the other lectures you have heard or learned something about the implied volatility.
No, sir.
No? Okay.
No, sir.
Okay, so then we come back after we have derived the Scholes formula. We will see how implied volatility is defined and used.
Sir, is there any difference between volatility and implied volatility?
There's a difference between volatility and implied volatility. I mean,
can you explain it, sir?
Yeah, I will explain it. So yes. Implied volatility is a volatility, such that if you put this value in the Scholes formula, you get the option price. You observe option price in the market, and of course, as I said, so this option, the Scholes formula is only valid under all these assumptions, which of course, even if the trader to some extent uses Scholes formula, he will get an idea about the price, but he will do add-ons, and then he get a new price, and the market price, if you then put in the volatility, the implied volatility in the Scholes formula, then you get the market price. You don't measure it statistically, implied volatility, you measure it from You calibrate it, as you call it. It's a calibration from market prices. It's very different from, let's say, observed volatility of stock prices. I'll put it like this. The observed standard deviation of log returns of stock prices are usually much lower than the implied volatility.
Sir, which one is better?
Implied volatility is usually it's larger. Implied volatility. No, but this depends on the market. There might be markets where implied volatility is lower, but in general it should be higher.
Yes.
And of course, implied volatility depends on maturity and depends on strike price. We will do this also probably in this tutorial. Okay. So there are now several ways. What we now want to do, that's a Scholes partial differential equation. This is we want now to calculate. For some function f. Okay, you can do it just by integration. If you do this, what I somehow sketched a little bit when I did the approximation of the CRR. How you calculate if f is the payout of a call option. This is then the Scholes formula. This is D1 and D2 normal distribution and so on, which I told you should learn it by heart. Okay. Now we see the connection to partial differential equation. So we now we take just f to be continuous. It's not bounded, so that's it's important, as we have seen, doesn't follow from the V-convergence of the CRR model. We take some growth conditions, continuous growth conditions. And then we look at this VT. That's what we want to analyze. The value of the option. Of course, we are mainly interested in at t equals 0. Or not. We are interested in this VT, the value of the option, and V0 is the current price. Okay. So if we look what at ST given S capital T given FT, we have the same, we have just time T minus T more or less, WT minus WT, it has actually the same distribution like WT. So in distribution, it's the same as WT minus T. Okay. Now we do this calculation, and we take now, we can say, okay, we define now Vt, so the stochastic process, as a function V, which depends on T and on St, because the conditional expectation is like this. This is actually, I mean, it might be clear, but it's kind of so Vt of omega equals small vt of st of omega. So if you do it generally at the beginning, so conditional expectation ft might depend on all information you have up to time small t, but basically because it's a Markov process, this underlines it's a Markov property, that this depends only on the state. This is small t. That's Markov. In general, it's Markov, but here you see it's Markov. But it comes with this statement here. You have written Vt like this one, because if you condition on Ft, you just have to put in the value of St here. So this means Vt, capital Vt is a function of, as a random function just from the path, from the value of S at time t. That's capital T. Yeah, so if we now know, and that's the Scholes PD, how can we characterize a function small vt of x? And that's a connection of the general theory gives you this, or that there's a connection between stochastic differential equation, and partial differential equation. And this, in mathematical finance, you only usually look at this one, but it's a general theory how you can solve partial differential equation by stochastic. Partial differential equation, how you can solve or how you can represent their solution as integrals, path integrals, if you like, over diffusion processes. So connection between diffusion and partial differential equation, it's a general concept, which appears also in physics and other applications of where you apply PDEs and stochastic differential equations. Goes back, for example, SDEs. Let's say Markov processes are related to Markov processes. There's also a broad area still of research. Markov processes are connected to partial differential equation. A particular one, the second order linear PDEs. Typical one is like heat equation. So the heat equation is strongly related to Brownian motion. And so actually the original Scholes paper, there's not much about probability, because they just work on partial differential equation. They more or less derived this partial differential equation by economic arguments in the original paper. They said, okay, if we have an arbitrage-free market, and if the price is a function of the current state, then the price has to obey this partial differential equation. The probability theory tells you, okay, that's correct. V is a function of the state only, and V satisfies this partial differential equation because it's this path integral, so this expectation under the risk-neutral measure. So the risk-neutral measure gives you R, and so sigma is still here, and so the partial differential equation. So this means the price, or the price function, put it like this, what would be the price at time t if underlying stock has value x? This we call now our price function v. This price function solves a partial differential equation. And for this we have to apply Ito formula. Yeah. The E2 formula, no, we apply, we now believe to some extent that V is in C12. No? Here we have our pi, here we ST is also positive. No? And this one is our time. It's a function of time and space. And space in our case is the state space of the process, it's positive. Okay, so we apply the E2 formula. Yeah, we have the two-dimensional E2 formula actually. So what happens with this entry? No? That's of course a very strange stochastic process. It says quadratic variation 0. So we only need to have the first derivative with respect to du. No? Then we take the derivative with respect to the second one, dsu. Then we take the mixed one, yeah, and we take the quadratic variation. So quadratic variation, if you take t and st, that's of course 0. And quadratic variation of t is also 0. Because they are all fine. The identity function, it has no quadratic variation and it has no quadratic cross variation. So meaning the only one is the second derivative up to of v, and so we integrate by the quadratic variation. So that's E2 formula. No? It's a two-dimensional E2 formula, where the first dimension is not really a stochastic process, it's a deterministic function, and the second one SU. Okay. Okay, so we now collect everything, as we have done in some instances before. We look all the integration with respect to du. So this means we get this one. And the quadratic variation, the quadratic variation of the quadratic variation of SU first we have this term, dSU under the risk neutral measure is RSU du plus sigma SU W. Okay, this means dSU, we have RSU, which appears here, and we multiply it also with Vx. So this is the first term. This gets here. We also integrate by du. And the quadratic variation of this one, we see 1/2 sigma square SU square Vxs. So that comes from the quadratic variation. And that's how you proceed in even more general ones. The quadratic variation, sigma square. You need a d. That's also what I skipped, because I couldn't do too much stochastic analysis. So if you have a stochastic integral, the general statement is quadratic variation. You get a stochastic integral, general one. The quadratic variation of this one is always HU squared times the quadratic variation of mu. This formula we apply to Brownian motion because U is quadratic variation of Brownian motion. Okay. So you see in this derivation, if you take it properly, you need some knowledge of understanding of stochastic calculus at least in the Brownian case. Huh? Okay, so this means we get from the quadratic variation, we get this term. This term we get from the quadratic variation. No? And then the only remaining integral with respect to Brownian motion comes from a stochastic process, comes from this equation, sigma, first derivative of v into x su. So that's now our stochastic equation, following from the Ito formula. Okay, this was Vt. Now we have to apply the Ito, the product formula. What is product formula? Yeah, if we know the equation for Vt, yeah, and then we multiply it by E minus RT, we get an equation of dt. Now the product formula. Have you heard about product formula in Ito calculus? The product formula, I showed you one specific product formula already. Noting by product formula, by product rule. So that's more or less a specific Ito for, we have two variables, f of x, comma y equals x times y. And then we have, you see the mixed derivatives. You take the first derivative, equals x0, y0 plus integral. First derivative with respect to y gives you x. So that's the same derivative with respect to x gives you y. Mixed derivatives gives you 1, so this one remains. Second derivative to x is 0, second derivative to y is 0. That's the product rule. And this we apply here, so you see we get new drifts. We collect everything again. So we get here, we get all integrals with respect to w, and the drift coefficient looks like this. From this product rule, the drift coefficient is a minus ru, and you have this equation. So as an add-on to this one, vt remains, this remains, this remains, and you get, with natural, you get also this from the discounting. Minus I. Okay, so what's called the drift, that's what you integrate with du, that's a drift, drift coefficient in terms of diffusion process. Is this one. Okay, at this stage, we now apply the knowledge that dt is a martingale. This means there's no drift. So this one is anyway a martingale. If dt is a martingale, this should also be a martingale, but this is of quadratic variation 0, so this cannot be a martingale. It's only a martingale if this one is 0. In this sense, in diffusion setting, martingales have no drift, or drift equals 0. So drift coefficient must be 0. Okay, we have to show that from this equation, which holds which holds only P star almost surely for all t, we have to prove first, or to show that ST takes any value in R plus. ST support is R plus, and V in C1 implies that this must hold actually T x for all x. So we have still here the step mathematically from almost P star almost surely to Tx all, to all Tx. So I said we have to, this comes that the support of ST is the positive numbers, and that these are all continuous functions. So it first holds a Lebesgue almost surely for t and x, Lebesgue almost surely, but then because it's continuous, much hold for everything. Because these are continuous function. But this is first a continuous function which is 0 on a dense subset, so it must be 0 everywhere. Okay. Okay. I mean, in order to show that V is in C1, 2, in this case, we actually need the property of the transition density. Is some integral of the transition density. Transition density of Brownian motion. And the transition density of Brownian motion is very smooth. We have something like x squared. So very smooth. So we can differentiate. That's some analytic arguments. Again, you have to do some integration with respect to Brownian densities. You need some properties of f, that they can be interchanged, but we have the necessary properties that the continuity, because it's an integral with respect to x, this is nice in x. If you integrate it, you still get a nice function in x. Put it like this. Because this is very nice, very smooth. Okay, so this means that's our Black-Scholes PDE. Now here you see we didn't use only in this case. Here we took our f. And some we took our f. And so, but here f does not appear. It's just a boundary condition which we have. Because this, we know by definition that v t of x equals f of x. So Black-Scholes partial differential equation is a boundary value problem, but at a boundary capital T. So from the uniqueness, we again prove based on the properties we have from f. Just to show you shortly, not in detail, but just shortly, why you.
Sir, we may, it's already 1 hour, so we may have a break of 5 minutes if you wish.
Yeah,
and then
that's
we can
fine,
start.
Yeah, then we can start again in 5 minutes. Okay.
Yes, sir.
Thank you very
Thank
much.
you so
So
much,
see you
sir.
in
Yeah.
5 minutes.
So,
Okay.
yeah, all
Bye.
the participants, please be joined. We'll meet after 5 minutes. Thank you, everyone. Please be here.